Hello my dear students, good morning to you all. So, in my last class I was explaining about what are the spectral distributions of black body radiations, right, and the characteristics of the curves which are observed in the distribution of energy in the spectrum of a black body. And next, failure of classical mechanics to explain the spectral distribution of black body radiations, and later on we understood how the Planck's quantum theory of radiation, which was invented in the year 19,000 by Max Planck. So, it helped us to understand the black body radiation in a better way than compared to the classical mechanics. So, there we saw mainly 3 postulates, and with the help of those observations, so those 3 postulates, so Planck gave expression for the energy radiated by a black body, which was corresponded to the length of a wavelength, that is lambda. And later on, so what is meant by heat capacity of solids, and with the help of that, so we gave explanation which was based on the Planck's quantum theory. That means how the quantum mechanics or quantum chemistry helps us to understand the heat capacity of all the monoatomic solids, so that is metals. So, that explanation was understood by using the concepts of Planck's quantum theory, and also we used Einstein concept. So, Einstein, by using the concepts of Planck's quantum theory, the equation or the formula which he gave for the heat capacity of solids at a constant volume was found to be a very good account. It gave a very good account. That means the equation which was given by Einstein. So, that equation supports the experimental observation that as temperature approaches 0, the heat capacity of the solids decreases to 0. Okay. So, this is where we stopped in our previous class, and in this session we will understand another important phenomenon in physical chemistry. So, that is what is called as a photoelectric effect. So, this photoelectric effect was discovered by Heinrich Hertz in 1887 and explained in 1905 by Einstein. So, let us see a brief history about this photoelectric effect. So, we all heard about a name, that is J.J. Thomson. So, J.J. Thomson observed that when light of a certain frequency falls on the surface of a metal electrons, so or a metal, what happens is so electrons are ejected from the metal, and this phenomenon is known as the photoelectric effect. So, here a clear animated picture is there in my first slide. What does it is going to explain about? So, here from this arc lamp, a radiation energy or a light of certain frequency is made to fall on a metal surface. So, this is the thin metal foil. When a light of certain frequency falls on this thin metal foil, so what happens is the electrons are ejected from the metal and it is collected in the collector. Okay. So, there we can measure how many electrons has been collected, and the whole setup is connected with the battery. So, which is having a variable voltage. Okay. So, those electrons which eject from the metal foil, so those electrons are called as photoelectrons. So, these ejected electrons which are called as photoelectrons, so they have an important note, that is the emission of these photoelectrons and the kinetic energy of the ejected photoelectrons is dependent on the frequency of the light that is incident on this thin metal foil. That means, so here the emission of the photoelectrons and the kinetic energy of these ejected electrons which are ejecting once after falling on to the thin metal foil. So, they depend upon the frequency of the light of the incident light on the metal surface. So, the process through which photoelectrons are ejected from the or from the surface of the metal due to the action of light is commonly referred to as photoemission. So, here you understood what is meant by photoelectric effect, okay, and what are photoelectrons and what is photoemission. So, three important terms you have understood here. So, this is very important to understand photoelectric effect. Okay. So, as I said, when a light of certain frequency falls on the surface of a metal, so electrons ejected from the metal, and this phenomenon is known as photoelectric effect, and the ejected electrons are called photoelectrons. A few metals show photoelectric effect under the action of visible light, but many more show it under the action of more energetic ultraviolet light. Okay. So, this is again a figure which demonstrates or which shows emission of electron by impact of light radiations. Okay. So, these are called as electron emission or photo emission. Next, what are the experimental findings of the photoelectric effect? So, these are the observations which were made after careful studies of photoelectric effect under different conditions. What are those? So, the first one, for each metal a certain minimum frequency of incident light is required to eject the electrons. That means, even for each metal there should be a minimum frequency of incident light, then only the electrons are going to get ejected from that metal surface, and that amount of minimum frequency is referred to as threshold frequency, or it is represented as nu naught. So, nu naught is called as threshold frequency, and how you are going to define threshold frequency is, so for each metal a certain minimum frequency of incident light is required to eject the electrons, and this is known as threshold frequency. And the second observation which was made based on this photoelectric effect was, a light of smaller frequency than threshold frequency cannot eject electrons. The threshold frequency is different from different metals. Not all the metals will have similar threshold frequency. Okay. So, that means, so the second observation says that a light of smaller frequency which is less than the threshold frequency, so it cannot eject any electrons. And the third observation was, so the kinetic energy of emitted electrons is independent of the intensity of the incident light, but varies linearly with its frequency. So, here the third observation clearly speaks about the kinetic energy of the emitted electrons. As I said in the beginning, so here it is very important to note that the emission of photoelectrons and the kinetic energy of the ejected photoelectrons, it is dependent on the frequency of the light that is incident on the metal surface. So, the kinetic energy of emitted electrons is independent of the intensity of the incident light, but it is going to vary linearly with its frequency. So, kinetic energy is independent of the intensity, whereas so it linearly depends upon, or linearly it is going to change with its frequency. So, this was the third observation which was made. And the fourth observation was, the number of ejected electrons from the metal surface depends upon the intensity of the incident radiation. Greater the intensity, so the larger the number of ejected electrons. So, suppose, so the intensity of the light which is made to fall on the metal surface is larger, then definitely the number of ejected electrons is also more. So, that is what I made a statement, that greater the intensity, so the larger the number of ejected electrons. So, these are the important observations which were made after the careful studies of photoelectric effect under different conditions. Now, let us understand what is the reason for the failure of classical theory to explain photoelectric effect. So, as we saw in the first introduction class of this quantum mechanics, so there we understood that, so classical mechanics or classical wave theory cannot explain the phenomenon of photoelectric effect. Why it does not explain the photoelectric effect is because, so according to the classical wave theory, energy of light depends on its intensity, right. So, according to the classical mechanics, so the energy of light depends on its intensity. In this view, it is correct that then light of any frequency is made sufficiently intense can cause emission of electrons. Okay. So, if that was true, that means according to the classical wave theory, so how the light is understood, energy of light depends on its intensity. If this view is correct, then light of any frequency if made sufficiently intense can cause emission of electrons, but this does not happen. But this does not happen actually, practically speaking. So, this does not happen. So, the quantum theory of radiation gives an easy explanation for photoelectric effect. Okay. So, that is why, so we are going to use so the quantum theory to understand the photoelectric effect. So, in my next slide we will understand how the explanation of photoelectric effect is given by quantum theory. So, this is also called as Einstein's explanation for photoelectric effect. So, this is also called as Einstein's explanation of photoelectric effect. So, as we all know, the photoelectric effect is a phenomenon where electrons are emitted from the metal surface when the light of sufficient frequency is incident upon. So, the concept of photoelectric effect was first documented in 1887 by Heinrich Hertz and later the Leonard in 1902, but both the observations of the photoelectric effect could not be explained by Maxwell's electromagnetic wave theory of light. Okay. So, that is why we consider Albert Einstein's explanation which was given to photoelectric effect by applying Planck's quantum theory. So, Albert Einstein explained the photoelectric effect by applying Planck's quantum theory. According to this theory, light consists of bundles of energy called as photons. The energy of each photon being equal to h nu, where nu is the frequency of light, correct. So, this is what we understood in our previous class, where while discussing about Planck's quantum theory of radiation. So, there we saw that so a light, according to this theory, a light, it consists of bundles of energy which is called as photons, and the energy of each photon being equal to h nu, and nu is the frequency of light. So, when the photon of light of frequency, that is nu naught is nothing but threshold frequency, strikes an metal or strikes an electron in a metal, so it imparts its entire energy to the electron. So, this energy enables the electron to break away from the atom by overcoming the attractive influence of the nucleus, and thus each photon can eject one electron. Okay. So, this is very interesting now. So, according to the Albert Einstein, he assumed that light acts as a photon or quanta, and one photon react with one single electron. So, photon give their all energy to the electron, and that energy is equal to the threshold value which is used up in the release of electron, and the remaining energy is stored as the kinetic energy of the electron. Okay. So, this was the explanation which was given by Einstein to explain photoelectric effect by using Planck's quantum theory. So, when the photon hits the metal atom, it transfers its energy to the electron. Energy equal to threshold value is used up in the release of electron, and the remaining energy is stored as the kinetic energy of the electron. So, the quantity h nu naught is called as work function or threshold energy. Suppose if h nu is the energy of the incident radiation, then Einstein applying quantum theory showed that h nu is equals to h nu naught plus half mu square. So, this half mu square is nothing but kinetic energy, right. So, h nu naught is called as work function or threshold energy, and h nu is the energy of the incident radiation. So, in this equation I am explaining the terms of this equation. So, here h nu is the energy of the incident radiation, h nu naught is the work function or threshold energy, and half mu square is nothing but kinetic energy, which is equals to half mu square, and this will be equal to h into nu minus nu naught. Therefore, I can write as kinetic energy is equals to h into nu minus nu naught. Okay. So, this equation shows that the kinetic energy of the electrons emitted varies linearly with the frequency of the incident radiation. So, a graph of kinetic energy of the photoelectrons versus frequency of the incident radiation will be a straight line. So, this is the graph. So, if you observe this figure, so this figure gives us the information about variation of kinetic energy of photoelectrons emitted with the frequency of incident radiation, and what observation was made was so the kinetic energy of the photoelectrons versus frequency of the incident radiation will be a straight line. So, that means that so here the kinetic energy of the electrons emitted varies linearly with the frequency of the incident radiation. So, that is why we are getting a straight line here, since it is in the linear, the variation is observed linearly. The slope of the line thus obtained is equal to Planck's constant. So, here the slope, if we calculate the slope of this straight line, so the value or the slope of the line thus obtained will be equal to the Planck's constant. Okay. This provides a method to find the value of Planck's constant. So, this calculation which we made by using this figure. So, where the variation of kinetic energy of photoelectrons emitted with the frequency of the incident radiation. So, this provides us so to find out a method to find the value of Planck's constant. The minimum energy just sufficient to liberate electrons from the metal surface with zero kinetic energy is called the work function of the metal. Okay. So, what is meant by work function means so that is the minimum energy, or in other words minimum energy is nothing but the threshold frequency. So, how much minimum energy is required or sufficient to liberate electrons from the metal surface with zero kinetic energy. So, the kinetic energy will be 0. Okay. So, if we consider the kinetic energy as 0 and how much minimum energy is required for that particular radiation or light to liberate the electrons from the metal surface is called as work function of the metal, and it depends on the material and the nature of the emitting surface. Okay. So, as I said, so this threshold frequency or the smaller frequency which is required is different from different metals. So, that is why so the work function of the metal depends on the material and the nature of the emitting surface. Presence of impurity layer on the photosensitive metal surface increases the work function of the metal surface. Okay. So, suppose if there is a impurity layer which is present on the metal, that is which is called as photosensitive metal surface. So, this increases the work function of the metal surface. Okay. So, in this way a clear explanation of photoelectric effect was given by Einstein by using the Planck's quantum theory. Okay. So, that is why quantum chemistry or quantum mechanics was capable to explain what and all the phenomena which were failure or which could not be explained with the help of classical mechanics were easily explained with the help of Planck's quantum theory, and there is a role of Einstein also to deduce his equations, because so in my previous class we saw about black body radiation, right. So, there also sorry, in the heat capacity of solids. So, while explaining about heat capacity of solids, there also we saw that Einstein gave a equation or a formula by using the concepts of Planck's quantum theory, and that was a very good supportive experimental observation. Okay, so that accounts that heat capacity of solids in a better way, and the justification was made with the help of Einstein's equation or formula which was given. In the same way, to understand this photoelectric effect, if we consider light energy as a continuous wave or continuous manner, then it is a failure. That means we cannot explain the photoelectric effect in a better way by considering the classical theory. Whereas, if we consider the energy of light, or light which consists of bundles of energy which were called as photons or quanta according to the Planck's quantum theory. So, if we imagine energy or light in this way, so then definitely we can give a clear explanation to understand the photoelectric effect by quantum theory. Okay. So, in this way photoelectric effect is understood according to the Planck's quantum theory. Okay. So, I am going to stop it here, and in my next class we will see another important effect which is called as Compton effect. Okay. So, what is meant by Compton effect, and how the classical mechanics or classical theory fails to explain this Compton effect, and what are the comparative studies of photoelectric effect and Compton effect in my next class. Okay. So, thank you dear students.